Okay, so just to recap what we've done so far in this unit, we started off talking about kind of the basics of motion, describing motion. We talked about what position is, what distance and displacement are. We talked about, what's the difference between speed and velocity? How do you calculate average speed versus average velocity? We solved some problems with constant velocity, right? Remember, we have the S equals V times T equation for constant velocity, and then we looked at problems with constant acceleration, where we have 4 equations for constant acceleration problems, and a specific type of motion with constant acceleration is free fall. And so the last thing we did is look at free fall problems. So far the emphasis has been on solving problems with equations, and today we're going to start focusing on analyzing motion graphs, which basically just gives us another means to solve the same types of problems without just using equations. So to kind of lead us into looking at motion graphs, I have a simulation which I want you to play around with. Okay, so I will include the link so you can access that simulation. And what I want you to do is open up the Moving Man simulation, and I want you to click on Charts at the top. And I want you to play around with the simulation by changing the position, velocity, and acceleration of the man just to different values, big values, small values, positive, negative values, and then when you click play, you should be able to see the graphs get created. And some of the things I want you to look at are how do the shapes of the position time and the velocity time graph change with and without acceleration. Okay, and when I say without acceleration, I mean that the acceleration is just 0. What happens if you have a positive velocity and a negative acceleration? And then vice versa, what happens if you have a negative velocity and a positive acceleration? Okay, so take a few minutes to play around with that simulation and see if you can answer those questions. Okay, so hopefully one of the things you noticed was that when you have motion with constant velocity, the graphs look kind of different than they do with constant acceleration. Now, for example, if you're looking at an object that's moving with constant velocity, its velocity time graph would look, well, constant. It would look horizontal, okay, because constant velocity means the velocity is not changing. And so the velocity graph would look something like this. Whereas the position time graph, or what we'll call the displacement time graph later on, it's the same thing, would look kind of linear. Now it could be going up or it could be going down based off of whether there's positive or negative velocity. Now remember that whether positive or whether velocity is positive or negative has to do with which way the object is moving. Right? Velocity is a vector, so it has magnitude and direction, and typically the magnitude is just the number part, and the direction typically is indicated by the sign, whether it's positive or negative. Now, when you add acceleration into the mix, okay, by definition, an object that is accelerating is experiencing a change in velocity. And so you can see how the velocity time graphs change. In the case of constant acceleration, the velocity time graphs become linear, right? Meaning they have a constant slope. The position time graphs, or the displacement time graphs, on the other hand, become curved. And the nature of this curve, we'll kind of look at that later, but actually, with constant acceleration, those graphs are actually parabolic, meaning that the curve is the shape of a parabola. And just to kind of tease that in, remember that one of the constant acceleration equations is ut plus 1/2 at squared is equal to displacement. And so if you think about this equation, if you had displacement or position on the y-axis and then time was your independent variable on the x-axis, this is the equation of a parabola because it's a quadratic. It's a polynomial of order 2, and the graph for that typically looks like a parabola. Okay, and so that's why with constant acceleration, those graphs are parabolic. Okay, whereas, velocity time, if you have constant acceleration, if velocity is is on the y-axis, right, as your dependent variable, and time is on the x-axis as your independent variable, then this is basically just kind of like, y equals b plus mx. That's just the equation of a line. Okay, and so you should be able to tell by looking at different types of motion graphs whether this object is moving with constant acceleration, whether it's moving with constant velocity, whether it's not moving at all. Okay, so let's talk about the three types of graphs that you're responsible for being able to understand and interpret. Okay, so the first one is what they call in the IB a displacement time graph. Now, often these are written as position time graphs, but displacement is basically just final minus initial position. And so as long as you have a situation where the initial position is 0, you can think of a position time graph and a displacement time graph as the same. And these graphs basically show how an object's position changes with time. So think of an object moving back and forth along a number line, and the y-axis is just that number line. So if you see on a displacement time graph, if the graph is going up, that doesn't necessarily mean that the object is physically moving up. It just means that the object is moving in the positive direction. And likewise, if you see the graph start to go down, that doesn't necessarily mean that the object is physically moving down. It just means it's moving in the negative direction. Now, I have bolded and underlined the most important thing that you need to know about displacement time graphs, and so here it is. On a displacement time graph, the slope represents the velocity of the object. The slope on a displacement time graph at any point represents the velocity of the object at that time. And the reason for that is you should have learned in math that when you look at slope on a graph, slope basically indicates rate of change. Velocity by definition is the rate at which an object's displacement changes over time. And so, if you connect those two concepts, it should make sense that on a displacement time graph, the slope represents the velocity. Okay, so if you needed to, figure out what the velocity of an object is given a displacement time graph, you would just, go to that time and find the slope at that point on the graph. Okay, now the second type of graph that you need to be aware of is what's called a velocity time graph, which is exactly what it sounds like. It's simply a graph that shows how an object's velocity changes with time. I do want to point out a few things. Number one, the difference between speed and velocity. So remember that speed is basically just the magnitude of velocity. It's just the number part of velocity. For example, if I'm in a car going, 50 miles per hour north, then the 50 miles per hour, that's my speed. And the north is my direction. And so the whole thing together would be my velocity. Also, make sure you understand what coordinate system you're working with. If an object has a positive velocity, it's moving in the positive direction. Okay, if it has a negative velocity, it's moving in the negative direction. If the velocity becomes 0, that means the object is not moving at that point. Okay, again, I've underlined and bolded the key information you need to know about velocity time graphs. So here it is. Number one, the slope of a velocity time graph represents the acceleration of the object, okay, at every moment in time. The slope on a velocity time graph represents the acceleration of the object at any moment in time. Number two, the area under a velocity time graph represents the displacement of the object. Now, what do I mean by area? Well, what I mean is, let's say you had a velocity time graph, like so, and let's say the graph was some crazy shape like this. I don't know. When I say area, what I mean is that it is literally the area between the graph itself and the x-axis, which is in this case is the time axis. So if I were to shade that in, it would be this area right in here. Okay, between the graph, bounded by the graph, and the x-axis. I'm doing my best to shade this in. Notice, by the way, you can have negative area if you go below the x-axis. So this area in here as well counts. Okay, notice I'm not like going over here because when I say under the graph, I mean again between the graph and the x-axis. That's what I mean by area. Now you might be asking yourself, like, how would you find the area of this weird curve-looking thing that I just randomly drew? Well, for that you would need calculus. And so typically in problems involving motion graphs, where you need to find the area under a graph, you'll typically be given really simple graphs that, where the area is just like a square or a rectangle or a triangle or something like that you know how to find the area of. Okay, but again, to actually find the area for, any type of function, you would need calculus for that. Okay, that's one of the reasons calculus exists. So it's very common to see problems involving velocity time graphs because there's two different key elements to look at, or really three key elements if you include velocity itself. You can look at the slope of the graph, you can look at the velocity itself, or you can look at the area under the graph. And so I would say that the most common type of question involving motion graphs probably involves velocity time graphs for that reason. Just because, given a velocity time graph, I can ask you lots of different things about either the acceleration or the velocity or the displacement. Okay, so pause there if you need to finish adding that to your notes. And then the last type of graph is the acceleration time graph. Okay, that shows how an object's acceleration changes with time. Notice, by the way, that positive acceleration does not mean an object is speeding up, just like negative acceleration does not mean that an object is slowing down. Alright, I never said that. All I said was that acceleration tells you how much your velocity changes by each second. Okay. Now, I also want to remind you again that acceleration has nothing to do with which way an object is moving it. Okay, all it tells you is how much your velocity is changing by each second. Okay, acceleration has nothing to do with velocity. It has to do with change of velocity. Now, on an acceleration time graph, a lot of the times you'll see problems with constant acceleration on an acceleration time graph. Sometimes you'll see changing acceleration on an acceleration time graph. Equation-wise, you'll never have to solve any equation problems with changing acceleration, but you might need to see it on, or you might need to be able to solve those problems with graphs, because on an acceleration time graph, the key piece of information is that the area under an acceleration time graph represents the change in velocity of that object. And again, when I say area, I mean that the area bounded between the graph itself and the x-axis, which in this case is the time axis. Okay, so those are the three types of motion graphs you need to be familiar with. Okay, so most of this I've already talked about. This chart right here just kind of summarizes the different parts of the graph that you need to be looking at. So for a displacement time graph, the slope represents the instantaneous velocity. When I say instantaneous, I just mean at that instant in time. So for example, if you're looking at a displacement time graph, let's say you have a displacement time graph that looks something like this. Okay, notice that this graph has three different segments. It has a segment here, here, and here. So if I just pick a random point on the graph, like let's say right here, and I calculate the slope at that one point, the slope there would represent the velocity at that instant in time. Okay, so that's what instantaneous means. It just means the velocity at that one instant in time. Okay, so make sure you finish adding that to your notes, and then we'll look at some examples. Okay, so example 1 says describe the general motion of this object throughout its journey, and then calculate the velocity of this object between 0 and 2 seconds. When you're doing a problem with motion graphs, the very first thing you always need to do is look at what type of graph am I given. In this case, we're given a displacement time graph. We can tell by looking at the y-axis, it says displacement right there. Okay, and then we have time down here. Now, we want to describe the general motion of this object throughout its journey. So first of all, remember that on a displacement time graph, the slope represents the velocity. So when I look at this graph, the first thing I see is that it starts at an initial position of 0, and then it moves forward for 2 seconds with a constant velocity. Now, how do I know it's a constant velocity? Well, number one, earlier I showed you, how constant velocity and constant acceleration look different on displacement time graphs. But also remember that the slope represents the velocity, and a function that has a constant slope is linear. Okay, so the fact that this is linear, meaning it has a constant slope, tells me that during the first 2 seconds of this trip, this object has a constant velocity. Now, I can calculate that velocity because, well, it's just the slope of this line segment. So I can see right away that this graph goes up 2 over 2, and so that velocity would be 1 meter per second. Okay, I'm assuming you know how to calculate slope of a line. So the velocity for the first 2 seconds would be 1 meter per second. Now, in the next part of the trip, notice that the displacement is not changing, okay, which means that the object is not moving. Or you can think, what is the slope of a horizontal line? Well, the slope of a horizontal line is 0, right? Slope is rise over run, and if you don't have any rise, then you don't have any slope. Okay, so however you think about it, the object is at rest here. It's not moving. Between 2 seconds and 4 seconds, the object is at rest. Now, what is the object doing in the next segment? Well, from 4 seconds all the way to 6 seconds, okay, notice that this object is moving with a constant velocity again, but the velocity is negative because the slope on this displacement time graph is negative. Now, what you would not say is the object is moving down. Okay, remember that you don't need to look at this graph too literally. Okay, the graph itself is going up and down, but remember when we talk about displacement, that's just basically talking about like a number line, an object moving back and forth along a number line. So if you imagine a number line where this end is negative and this end is positive, the fact that the object has a negative slope means it has a negative velocity, and that basically just indicates that the object is moving this way on the number line. So, and I could calculate that slope, but I'm not going to just right now. But I know this object is moving at a constant velocity, and then it's at rest again between 6 seconds and 8 seconds, and then between 8 seconds and 9 seconds it moves forward with a constant velocity. And again, I could also calculate that, but I will just show you what the answer is. Okay, so the total description of this motion would look something like this. Okay, I put the text in red. Okay, so notice how specific my answers are. Okay, when I ask you to explain something or describe something, I want you to write in clear, coherent sentences, and I want you to be as specific as possible. When you're writing a question out, you don't want to leave any lingering what questions or lingering why questions. So for example, if I had just said, between 0 and 2 seconds, the object's moving with a constant velocity, a lingering what question would be, what is the constant velocity? Well, it's 1 meter per second. Okay, so specificity is important. Okay, make sure you're writing in clear, complete sentences. Okay, so let's go on to example 2. Pause it there if you need to finish looking at that. But example 2, it says look at the velocity time graph shown to the left. First question says describe how this car is moving. Questions asking you to describe motion. The only types of motion that you really need to be able to describe are being at rest, moving with a constant velocity, and moving with a constant acceleration. Now, are those the only types of motion that exist in the universe? No, definitely not. Okay, but because this is just, high school physics, we don't usually see super complicated types of motion. And so for the sake of answering questions like, what type of motion does this object have, either at rest, or moving with a constant velocity, or moving with a constant acceleration, those are usually going to be your answers. Okay, so I would look at this graph first. What type of graph is it? It's a velocity time graph. How would I describe how this object is moving? Well, number one, I would say this object is moving with a constant velocity. Now, how do I know that? Well, because this is a graph of velocity versus time, and I can see that the value is not changing. But if I were just to say, let's say my response was this object is, if I were to just say this object is moving at a constant velocity, then that leaves a lingering what question, okay? what is the constant velocity? Well, it's of 10 meters per second. Okay, so that's a more complete answer. Is this object accelerating? No. Okay, no, this object is not accelerating. How do I know that? Well, number one, constant velocity basically means your velocity is not changing, and acceleration by definition tells you how quickly your velocity is changing. Okay, so constant velocity and constant acceleration are mutually exclusive. You can't have both of those happening at the same time. If you have constant acceleration, then your velocity is changing by definition. And if you have constant velocity, that means your object is not accelerating by definition. Okay, now you could also say on a velocity time graph, the slope of a velocity time graph represents acceleration. What is the slope of this graph? Well, the graph is horizontal, and so that means it has a slope of 0 because it has no rise. We talked about that before. So this object is not accelerating, and then you would justify your answer using one of those two explanations I just gave. What is the displacement of this object after 5 seconds? Okay, so you just need to flat out memorize the different parts of the different graphs, and so you just need to know how do you find displacement from a velocity time graph. You find the area under the graph. Okay, there's no way to get around that. You just need to know that. Okay, so what does that mean? The area under the graph after 5 seconds. Well, when it says after 5 seconds, by the way, that doesn't literally mean after 5 seconds. It means that the time starts at 0, and after 5 seconds have passed, you're now at 5 seconds. So if I want to find displacement from a velocity time graph, I need to calculate the area under that graph. So the area, in this case, represents the displacement, S. And remember, when I say area under the graph, I mean the area bounded by the graph itself and the x-axis. So in this case, this area in here. This is just like a long rectangle, right? So that would just be 5 times 10, which is 50 meters. Okay, and so that's how you would use the velocity time graph to find the displacement of the object after 5 seconds. Now, of course, if you are paying close attention, digesting everything in this unit, you also have to realize that if it is constant velocity, then the constant velocity equation, S equals V times T, also has to apply. And so if you have the velocity of 10 meters per second times 5 seconds, that should give you the same answer. Okay, and it does. So again, solving problems with motion graphs is really just a different way to solve the same types of problems. Alright, so let's take a look at a couple more examples. Okay, example 3, it says look at the velocity time graph to the right. What is the velocity of the object at t equals 2 seconds? Well, this is a velocity time graph. So at 2 seconds, I look at the graph, and the velocity is 8 meters per second. It's right there on the graph. What is the displacement after 5 seconds? Now remember, on a velocity time graph, the displacement is calculated by finding the area under the graph. Notice, by the way, that the first thing you really should see from this graph is that based off of the shape, it's a linear velocity time graph. That means that this object is moving with constant acceleration. Okay, so just kind of keep that in the back of your mind. Now, the area under the graph would be the area of this triangle in here, right? I can't shade very well with my tablet, but that's a triangle. And so the displacement would be the area under the graph, which would be 1/2 times the base of 5 times the height of, let's see, the graph goes up to 20. So that would be 50 meters. Okay, so S would be 50 meters. Now, I also want to point out something. Again, because this is constant acceleration, all of the constant acceleration equations that we've seen so far have to also work. So notice that this object has an initial velocity of 0 meters per second from the graph. So if we have u equals 0 meters per second, and let's say we want to find S, and we have a time of 5 seconds, then I could use the equation S equals u times t plus 1/2 a t squared. Okay, now this would be 0, okay, because there is no initial velocity. We don't have the acceleration quite yet, but let's look at the last part of example 3. What is the acceleration of this object? Well, on a velocity time graph, you calculate acceleration by finding the slope. Alright, so this slope, I can see right away, that's going to be, the graph goes up 20 from 0 over 5, so 20 over 5 would be 4 meters per second squared. Alright, so now that I have the acceleration, I can go back to my equation up here, 1/2 at squared, a is 4, t is 5, and guess what this gives me? 5 squared is 25, times 4 times 1/2 is 50 meters. Okay, but again, the only reason that works in this case is because the entire situation is constant acceleration. Remember, my 4 equations only apply if I have constant acceleration. What I'm teaching you about motion graphs always applies no matter what. Okay, no matter what, the velocity time or the slope of a velocity time graph is always acceleration. Even if, by the way, even if the graph is not a straight line at every single point, even if it's a curve, okay, it's still true that the slope represents the acceleration on a velocity time graph. And now you could ask the question, I guess, how would you find the slope of a curved graph? And again, I will just tell you that's one reason that calculus exists, is to be able to calculate the slope of a curve. Okay, but that's not something that you need to worry about for IB physics. So pause it there if you need to take a look at that some more. Alright, so I think we're just going to do those 3 examples, and I will do a few more motion graph examples in class. As always, please let me know if you have any questions, and I'll see you guys in the next video.